relativistic fermions and algorithms for that. However, I come from a sort of a relativistic fermion community, and although the details of the questions or the complications of the problem are slightly different, the fundamental challenges are very similar. So we are also dealing with many fermion problems, and fermion sign problems are very important. Often we don't have a fixed node approximation that we can really apply. So if we ignore the sign problems that we have, we get completely wrong results often. And so there is actually a workshop devoted to why we get wrong results when we ignore fermions. So in the last, I would say, quite some number of years, I've been exploring if there is a different way to think about fermions and fermion sign problems motivated by quantum field theories in general. So I would say there has been quite a bit of success, although often people ask me, have you solved the fundamental sign problems? Not yet, but however the progress has been quite remarkable. I would say there have been new solutions that we can find which was difficult. In fact, people who have ignored the sign problem in the past have gotten wrong results, and we actually are able to correct some of these results, and I will explain some of these ideas to you. Of course, as we all know, Matthias is in the audience somewhere, hopefully. Yeah, there he is. So he and my old-time collaborator have shown that sign problems are in general difficult. If you solve all possible sign problems, maybe you even solve some NP complete problems. So one has to deal with sign problems with each problem in mind, one by one, and see if maybe there is a class of problems we can solve. And maybe these are not the class that is most exciting to us today, but still, if it is non-trivial progress, I think we should be able to acknowledge that. So let me, so here is the outline of what I'm going to tell you. I will review briefly about, which side do I point it? So I'll briefly review how we deal with fermions and quantum field theories. I'm sure many of you are aware of this, maybe some of you it's sort of new to them. Then I will take, basically we deal with fermions starting with Lagrangian formulations where fermions are represented with Grassmann integrals, and for almost, I would say, 30 years or so, the approach has been a fixed approach, right? And that's what we in the condensed matter community is called the auxiliary field approach. For us, often the auxiliary field is already the dynamical field, but then we can also deal with 4 fermion interactions using that direction. However, one can do these Grassmann integrations in a slightly different way. That's what I would like to explore here and motivate that there is a new idea that I've been exploring, which I call fermion bags. I will explain what that means. And then I will take a very simple model and explain to you why sometimes sign problems are hidden in this auxiliary field. One has to really be careful about introducing the auxiliary fields. And then I will show you a whole new class of solvable models which seemed unsolvable before. So in some sense, some real progress has been made. That's what I would claim, and you can judge for yourself. And I will show you some recent results that I've obtained with Anyi Lee, who is a postdoc here. And then I will present some conclusions. So let me begin with the review of fermions and quantum field theory. So typically, when we want to do some kind of problem, QCD or a 4 fermion field theory or anything, we start with a partition function which is written in terms of certain bosonic fields phi, and the fermionic fields are represented through Grassmann variables. And I'm sure even any condensed matter system can be rewritten in this particular form. This is quite general. And so the question is, when you try to do Monte Carlo simulations, one has to understand, what do you mean by Grassmann variables?
Well, what do you mean by Grassmann variables, period?
Yeah, so I'm going to explain to you exactly. So I'm sure, so this is exactly what a Grassmann variable is. Essentially, these are numbers which anticommute with each other. They are basically numbers, they're not operators. So, and then the square of each number is just 0. And the reason why you introduce these numbers is because if you try to write down the path integral starting from a C-dagger C type of creation annihilation operators, it's not clear what is the coherent state for a fermion. It's often difficult to write down, and so if you really write down the action, the simplest way to do that is to introduce these new anti-commuting variables, and then one can easily write down the action. And the action, basically these numbers, if you want, we will see in a moment, you will understand a bit more about what Grassmann variables are as we go along. You will see that these Grassmann variables are a very nice way to keep track of fermion paths. That's all it does. It's sort of the fact that the square is 0 tells you that two fermions cannot come on top of each other, and the fact that these two anticommute tells you that there is some kind of a fermion permutation. That's sort of a hand waving way of discussing what fermions, Grassmann variables are. Yes. Oh, sorry. So then the basic rules finally at the end of the day is to integrate over fermions. That's pretty straightforward. You don't have to worry about all the rules of integration. It's extremely straightforward. If you don't have a fermion psi, it integrates to 0. If you have a fermion there, it integrates to 1. So what has been used is that once you have these simple calculus of Grassmann variables, often we have many Grassmann variables, one Grassmann variable for every space-time point essentially, and if you integrate and every fermion degree of freedom, and if you integrate them out, the simplest kind of models are fermion bilinears of this type, and when you can basically integrate this whole thing out, you just get a determinant of this matrix. And that's sort of the hidden feature of all these Slater determinants. So instead of working with Slater determinants, if you want to work with an action, that's the kind of thing that you will introduce. So the traditional approach for a long time, I'm not sure even if these are the earliest papers I've been looking around, the earliest papers of how to do fermion integrations of this type were introduced by these authors here, and they suggest that if you have a path integral of that type, you basically integrate out the fermions, which is very easy to do, and then you deal with the bosonic system essentially. And then you try to think about Monte Carlo methods for sort of generating these sigma configurations using some distribution, right? And then the question is, if this determinant turns out to be positive, then indeed that will be your Boltzmann weight for each sigma configuration, and then you can try to generate all kinds of sigma configurations. And there are various variants of how one should do this. One, of course, you can use a determinantal Monte Carlo, but then the QCD community likes to use something called the hybrid Monte Carlo, and there's also been a lot of ways of rewriting this determinant now as a positive. Since it's positive, you can write it as a bosonic integral again, and then this is what is called pseudo fermions, and then one integrates over those new set of degrees of freedom. So for the moment, I will assume that once this is positive, the sign problem is solved. But however, remember that the sign problem can only be solved if this determinant turns out to be positive, and one has to calculate the determinant. And this calculation of the determinant is pretty complicated. If there are singularities of this matrix, for example, if there are 0 modes, this is positive, but there's no guarantee that this determinant is not 0. So if there are 0 modes, one has to calculate the 0 modes accurately, and that can cause a lot of trouble. So the fact that this determinant is not positive is being one of the fundamental difficulties. That's what we call a sign problem in our approach. Now, most solvable problems from our side have matrices that can, of course, remember this is a matrix, this is a bilinear, so I can choose a basis as I want, and so I can choose a basis where the matrix can be written in this particular form, where this is D and this is D dagger. It's exactly the same matrix with a minus sign, and so now the determinant of M can be seen to be completely positive. So all sign problems that are typically solved have the structure built in them. And so then determinant of M is positive, and one can then try to formulate Monte Carlo methods for that. However, many interesting problems are not of this type, and I will show you examples as we go along. Now, let me sort of explain the idea, what I'm heading at, with a very simple model. So suppose I have what I call a plaquette model. What I mean is there is my fermion free, this is what I call free fermion because it's just a bilinear, and it has a solvable form. What I mean by a solvable form is exactly this, right? So assume that this is something that I will come back to again and again. So assume that M is some matrix that has a solvable form. So that's exactly what I have. That's a free theory, let's assume, or maybe in some background field which I can then integrate out. But then in addition, let's say I want to add such an interaction. Now this is, you see, it's an 8 fermion interaction, maybe looked cooked up, but interestingly we will see that there are interesting questions that might be of interest when we introduce these strange interactions, because remember I am working in Grassmann space, so often a high fermion interaction means something like a repulsion or some kind of an interesting thing. If we can discuss this later on, but let's assume that we just add in this 8 fermion interaction, and now one can ask, how can I approach this particular problem? Now in the conventional approach, this is not of the type that I would like, so I would like to introduce an auxiliary field. And so what one can do is, when we write down the path integral, there will be an integral over this free fermion part, and then there is, since this is over every placket on a lattice, so for every placket I have this exponential of this term, and now I introduce a discrete auxiliary field which is just a Z4 field. This is e to the I pi by 4 essentially, all the phases of Z4. That means that pi by 2, sorry. That means that I can linearize these 4 fermion interaction, 8 fermion interaction can be made into a fermion bilinear by introducing this particular thing, and that's the usual Hubbard-Stratanovich transformation for such an interaction. And then the partition function takes the normal form that one would write down, that would be psi bar this matrix M, but now there is a diagonal matrix because of this term, and there is some kind of a sum over all the z factors that a particular site touches from all the plackets, right? So there is some term like this, and now that's a complex number. So now I'm adding to this M a term that is non-zero on the diagonal entries, and that can fluctuate. So now I have all these entries which are non-zero that fluctuates quite rapidly, and so now this determinant is no longer positive. So that's a simple way in which introducing an auxiliary field to solve this problem introduces sign problem. So the lesson that we learn from this is that introducing auxiliary fields without some careful thought can lead to sign problems, and I will show you that this particular model actually has no sign problem to begin with. There are other ways to approach Grassmann integration, and that is the question, that do we have to just integrate out the fermions by introducing an auxiliary field, or can we do something slightly different? So here is where let's take a look at what Grassmann integrations are about. One way to think about Grassmann integration is to think about them as generating fermion world lines. Now these fermion world lines are not quite the same as the world lines in the Hamiltonian formulation, but if you keep a careful bookkeeping, you may be able to match them, right? So they are not completely different, but there is a connection. You can make some connections, but the bookkeeping is slightly non-trivial. For example, every time there is a psi bar and a psi on, let's say, in site I and j, I just put a directed arrow. So for example, psi bar I, psi I on the same site would just be a circle on itself. Now I have a I, j, j, I will be a thing that goes from I to j and j to I. So that will be a loop, right? And remember that since the square of each Grassmann variable is 0, on each site I can only have one psi bar and one psi, and I do need one psi bar and one psi before the integral is non-zero. So whenever I have, and then things like an exponential of such a term just ends. It's a very simple polynomial, that's all it is. And then 1 means there's nothing there. Again, psi bar I, psi j means there is this directed arrow, and then if there is a weight, then I have to take that weight on that particular bond connecting it. So then the Grassmann integration is trivial. If you don't have a particular psi or a psi bar on a given site, then that integral will be 0. So I need to make sure that every site has one psi and one psi bar. And now if I have exactly one psi, the integral is 1, but then I have to keep track of how, oh, this is wrong. This should be d psi bar I, d psi I, and then psi bar, oh, this is this term, yeah, exactly. So if you have this term, then if I integrate out because of this loop, I get a minus sign, and again every loop leads to a minus sign. And these are basically the rules of Feynman diagrams, if you want, but occurring in a slightly different context here. So what this particular integral actually means is that it's a sum over all possible fermion world lines on your discrete lattice. Every site must have an incoming and an outgoing line. Every loop has a negative sign, and then there are weights, and then there is a sign factor, and the sum of all of these is exactly this determinant. So it's basically an expansion of determinants in terms of closed loops, right? Now that's a very useful thing to remember, that when in the traditional approach, when we do the determinant calculation, we are actually summing over all possible fermion world lines in all possible regions of space and time. Now is that necessary, or can we do some subset of regions where you sum over fermion world lines, and then if you choose those regions carefully, perhaps you still get positive weights? And that's sort of the basic idea of the Fermion bag approach. So the Fermion bag idea is to...
But it's a trivial statement, because when you write down, you see that propagate, you see that like there's nothing else by the propagate of a slater determinant, another slater determinant, and it's exactly what you have. You can explain that, you see, in a very simple language. You don't need Grassmann variables for that.
Fair enough.
It's exactly the same thing.
I completely agree with you. So I think...
But it looks like the image you're showing now, it's much more complicated, hidden behind Grassmann variables and so on. It's something very simple, really. It's an overlap, it's a trace, you see, nothing else, so that's what you get there.
Fair enough. Since I work in the Grassmann variable language, I find that simpler. But
it's not simple.
Okay.
It's not equivalent is not possible.
It's completely equivalent. That I completely agree.
Equivalent is true, but it's not simpler.
Okay. So what I'd like to do is that so as we go along, maybe you will see some of the applications in the Hamiltonian approach. Some of the things I find it easier here. So let me explain what my idea is. So if you group fermion world lines inside regions instead of really doing it over the whole of space-time, that region is what I call fermion bag, and if I can sum over them, and if I choose the bags carefully such that that integral over that particular region was positive, then maybe you can solve sign problems in different ways, and that's sort of the basic idea. And this is I would say an extension of an old idea that I and my collaborator proposed long time ago, but there it was pretty restrictive, and here I would say that my understanding of Grassmann variables helped me quite a bit in extending the idea much more broadly. but I agree that there is a complete connection with the Hamiltonian formulation. So let's consider a simple integral of this type, right? Where I have this is the exponent, and these are all not in the exponent, on the integral itself, right, on the on the line. So there are sort of terms like psi bar I psi I there. There is a 4 fermion term there. I2, I3, I3, I2. This is this loop here. There are all these various insertions, right? And now let's say I want to do this integral. Now if I do this integral, I can clearly group this separately, that separately, that separately. These are all separate integrals can be done, and because I have introduced sort of cleverly the sign factors in front of these things, all of these integrals are all just 1. And what about the remaining integral? Now the remaining integral has a psi bar m psi, where the psi and psi bar should not contribute to these sites, because we know that any fermion world line, as the way I told you, cannot touch that site, because that already has a fermion, a psi bar and a psi completed. So it's all saturated with fermion variables. So the remaining integral is just a path integral over the remaining space where these particular sites have been dropped. Right? It's exactly the same free fermion integral, except that these sites are dropped. So what I get is again a determinant. The determinant is of a matrix obtained by dropping the same columns and the same rows off from the matrix M. And that's exactly this Grassmann integral is telling me. So what that means is that if M had this nice solvable form, right? Zeros here, and some M and minus M dagger essentially here. If I drop same rows and same columns, I get a new matrix W, which is exactly of the same form, right? And that means if M is this, W is that with a slightly different matrix, which is a slightly smaller matrix than M, and then the determinant of W is just positive, right? So the fact that M was positive, M was a solvable form, I can have terms, insertions of this type, and this integral is again positive, right? That's what we learned from this. Now how does that help? So let's go back to the kind of things that we can solve. So now let's assume that there is an action which has a solvable matrix, but then lots of interactions, right? As many interactions as you want, and I put in interactions of that type. All of these we know when I expand in Grassmann variables will just pull down, will be polynomials, and every time I get a 1 or one of these terms, and as soon as I get one of these terms I can do that integral, it's going to be positive. So every such problem is completely solvable. There is no sign problem in any of these interacting problems. So one can easily introduce high fermion couplings, and these couplings, although look sort of artificial in the Grassmann language, they actually introduce all kinds of repulsion and all types of interactions that seem interesting. So let's now do the simple fermion bag approach to the placket model. The placket model, traditionally what I would have tried to do is to introduce an auxiliary field to make this bilinear, and then I just showed you that there is a horrible sign problem in that particular approach. But in this approach what I would do is just write this as 1 plus G, and then I know that for every placket I can either pick a 1 or this G term. So now I introduce a discrete field on each placket.
This is your case is exact, right? It's not approximate.
This is not approximation, this is exact.
Yes.
Yeah. So this is exact. So this is just a, if you want you can say I'm introducing a different type of an auxiliary field if you want. So but then the idea is slightly different, that you then have 1 plus G, and then you have configurations now of all these placket variables which are either non-existent or existent, and then one can then do the Grassmann integral. I just explained to you that this Grassmann integral, with wherever there are plackets, wherever these terms exist, all those terms are just dropped away, and then this turns out to be the determinant of some different matrix. That different matrix has a positive weight. So here is the same partition function where all the Grassmann integrations have been done. This is a discretizing type of model where you have regions where there are these plackets, these red are these interaction plackets, and then there are these other regions where the fermion can hop around freely, and there is a determinant in that particular region, and that region, that determinant is positive, and that's the statistical mechanics of that particular.
What is NP?
That's the number of plackets that's basically saying that how many such terms exist.
Or you can say it's a perturbative expansion of your idea.
Yeah, exactly. It seems perturbative, but on the other hand, notice I have not done any approximations on a finite lattice. This is exact. There's really no.
No, the translation is exact, but various terms have different signs.
I just argued there is no sign problem.
No, but different terms have different phases. You see, each term, you see, it will have the determinant positive, but when you put the interaction, you see, because you're having the coupling costs a different power, you see. So if it's positive, it's one sign. If it's negative,
Yeah. So here.
so you have a phase, you see.
No, but
depending on the order.
if you choose G to be negative, you're completely right. But I'm going to choose G to be positive, such that then there is no sign problem. You agree that for G positive, there's no sign problem.
It's the other way around. But
Okay, so for one sign of G, there's no sign problem, right?
that's correct.
That's fine. So that would be the traditional approach to do the problem, and here is the more sort of easier approach to do the same problem. And notice that as the G becomes larger and larger, there will be many plackets, and so the regions of these fermion, this is what I call a fermion bag. These red also in some sense are fermion bags. They are basically interacting bags. the main difficulty in the computational cost is calculating the determinants of these regions, and if these regions shrink, then it becomes much more easier to do the fermion to do the calculations. So that model that I introduced was just a toy model to explain the idea of a fermion bag. Now let me explain to you that there is a whole new class of problems that we can actually solve using this approach. So what type of models are these? So consider, I always begin with a system where I can solve the sign problem. So this M is in the solvable form, right? And now I introduce an interaction with a complex phase, basically a scalar field interacting with an on-site psi bar psi kind of term, right? And that is a coupling G there, and then there is some action for the sigma and the phi, and now I am assuming that S, the bosonic action, has a solvable form. Now what does that mean? That means that whenever I get a correlator of this type, so remember this is the action that I have for the bosonic fields. If I want to do this path integral over all the phi degrees of freedom, that is positive and can be expressed as a sum of some other maybe fields where everything is positive. So what I mean is, for example, remember these are all complex fields, so if I want to do this integral using Monte Carlo, that's going to be horrible, right? It has all kinds of sign problem because these are all positive and negative fluctuating, and k can be very large if you want.
You don't impose hermiticity?
No, as long as this is positive, I'm fine. So the action often, for example, with a chemical potential.
No, you see, forget about the chemical potential. I'm talking about the interaction.
This interaction?
Yep.
This interaction is exactly what I've written. There is a G, which is a real G.
Hermitian. It should be Hermitian always. Because otherwise you don't conserve the norm, you don't conserve the norm.
Remember, I am in the action formulation, so the hermiticity is a bit complicated to understand because there is a transfer matrix, and one has to think about the transfer matrix.
Rewrite it in the usual second quantization form. It has to be Hermitian.
So all you say will emerge completely carefully when we do the second quantization. This is the basically mass term in QCD. You always write that down, and you can actually show that this is exactly the Yukawa coupling in field theory models. This is exactly the Yukawa coupling.
If phi is real, not complex.
No, even if phi is complex, that's perfectly reasonable because you can actually transform psi and psi bar using phases and show that this particular thing is.
No, the phases to be complex conjugated because they're on site.
Oral, psi bar is not the conjugate of psi. They're independent variable, Grassmann
But
variable.
if you're writing in second quantization, they are.
So in a relative
So you
theory, you can
rewrite
take-
it in second quantization, you see they should be real.
In the Dirac theory, the mass can have a phase and it's completely equivalent. So it's
Okay.
parallel rotation.
Yeah, exactly. Fair enough. If I can always rewrite, give me a problem, I can rewrite such. I'm just giving you a class of problems, right? So if I really think about a particular action, I will show you exactly that everything is everything obeys hermiticity, everything is fine. Of course, you're in a lattice field theory, so hermiticity should be understood in terms of the transfer matrix and the and things like that. So what I mean by the solvable bosonic theories are that you have this G which is expressible as a sum of maybe some other set of fields where omega is positive. Right now this is something that needs to be done before one can really solve the sign problem, and since it's just a bosonic correlation function, I assume that many of you will agree that this is doable, but if you have questions, I'm happy to sort of give you examples of where this can be doable. For example, on a 5-4 theory, this is completely doable. There are XY models where one can do it. So there are lots of interesting field theories where this is completely fine. There's really no problem with this. So once that sign problem, this is the bosonic sign problem, this is what I call the bosonic sign problem. If that is solvable, which is usually the case in most cases, I'm not saying it will be true in all cases, but at least if you choose that in the solvable form, then these models will be solved, because what I can do is, of course, in the traditional approach, notice that there will be a sign problem in this case, because M sigma will have this strange structure G phi, phi 1 and phi 2 star. There's really no symmetry. The determinant of this has a sign problem. So this has been a bottleneck in most of the calculations of this type. But I will argue that the Fermion bag approach solves the sign problem completely. So in the Fermion bag approach, remember that I'm going to sort of expand things, this interaction in powers, like it's like 1 plus g. And so when I start with the path integral, there is a bosonic part, there is the free part, and then there is this interaction piece, and this interaction piece I add as 1 plus g as I did before. And now this has two parts, 1 and 0 and 1. So this nx takes values 0 and 1 exactly as we did for the placket case. Here it's not a placket, it's on on-site interaction. And then I can introduce this new discrete field which I call a monomer field. And with that field I can then rewrite my path integral where there are these powers at various x's. So I can have many different x's where n is non-zero. So for example, if I take a particular configuration where let's say there were x's that were non-zero in all these points, these are z1 to zk points, let's say, where n is 1 and everywhere else n is 0, then that particular term will look like that, where there will be k powers of g, and then there will be all the phi insertions of the bosonic integral. That is exactly what we said was solvable. And then there will be a fermionic integral, which I just argued was that since these sites basically get removed, the k point correlation function in the fermion is exactly a determinant of a matrix W where all these different sites have been dropped. So you, again, if M has a solvable form, W has a solvable form, and so the sign problem is solved. So in this new way of looking at it, the partition function is written in this new way where you have bosonic integrals, sum over maybe some monomer field and some other B discrete fields. There is a Boltzmann weight, and then the fermionic physics exactly is this determinant that depends on where the monomer fields have been, where the things are non-zero, and then there is a determinant of a particular matrix and that determinant is positive. So this is a nice way to rewrite the path and partition function as a statistical mechanics of some very interesting set of objects here, which are monomers, and there are other bosonic objects. But then the fermionic physics is hidden again in terms of determinants, and then there is no sign problem. So remember, again, the original problem had a sign problem, so the traditional approach would not have worked for these class of models. So again, what happens at large coupling? At large coupling, there are many small fermion bags. So the fermion bags are only in some regions. All the others have been taken over by these interaction sites. So at small fermion bags, the computation is efficient. But then one might ask, what happens at weak coupling? Because at the weak coupling, the fermion bags are big, and so it looks like a difficult problem, and that's true. Indeed, in principle, fermion physics is difficult. On the other hand, there is an interesting duality where the k point correlation function that we wrote down, we saw it with the viewpoint of removing Grassmann that is not doing Grassmann integrals on these sites, and then the remaining Grassmann integral being done in the remaining region. But then I can also use Feynman perturbation theory to really write down all possible correlators, and that's precisely again another determinant, and so there's actually a duality relation here. I'm sorry, there's again a mistake. So this is just W and this is just M times det. So this is the same as the determinant of W, which is just a relationship in linear algebra, and this is exactly the picture that condensed matter physicists have been using, called the diagrammatic determinantal Monte Carlo. So interestingly, at weak couplings, the problem is actually much simpler if I do it like this, because if there are, let's say, k monomers on an average in your system, it's much easier to do a determinant of a k by k matrix than on of a v minus k times v minus k matrix. However, at strong couplings, the other side becomes more interesting. So in some sense, I feel that the ideas that have been generated in condensed matter is much more actually broader. In this approach, I see that there is actually a duality. If something works at weak coupling, most likely it will also work at strong coupling, and maybe there are interesting questions one can resolve at both the couplings. So the lesson that I learned from this is that the sign problem, to solve a sign problem, the sign problem could actually be entangled in both fermionic and bosonic variables. We had to solve, remember I assumed that the bosonic thing was solvable, and then I had to sort of think about interesting ways to solve the fermion sign problem. Both need to be thought about, and a full solution may require one to solve both type of problems, and often the problem is that maybe you don't know the right variables to write down the bosonic theory, bosonic variables in, and that could be one of the ways of thinking about the sign problem. Yes?
I have a question. You talked about the cost. Is it just the cost of lots of determinants? So it's
Yes.
just n cubed?
Yes, yes. So it's a determinantal type of method. You can maybe make it better if you want by using hybrid Monte Carlo, which we have not yet tried, but at least for some problems it might work, but we have been using determinants. So yeah, it's just cost is exactly determinant. But in fact, the determinants are of the size of the bag, not the whole. So basically remember that, so when I try to update this, these are all usually local. The only non-local thing is that, but that depends on the size of this W if you want, or the size of this G.
I just, naively, that's not expensive in some sense, because typically we want n cubed anyway.
Right. So all I'm saying is this is slightly better than n cube in the sense that, of course, it can still grow with the volume. However, for example, in the strong coupling region, these bags can actually be pretty small, and so you can go very far with this method. So there are also other problems. So I just motivated one class of problems. For example, there are other problems, and these may be of more interest for non-relativistic fermions. For example, let's assume that M was of some of your of the favorite non-relativistic fermion form, but it had this interesting symmetry, which of course free fermions do, but there are also other interesting spin interactions that you can introduce in M that also introduce that, and there are also other symmetries one can talk about. I just talked about the simplest symmetry. If that was true, then we can prove that the determinant of M is actually positive. Then this is where you can actually show that the eigenvalues come in pairs, right? Real eigenvalues come in pairs. All eigenvalues are complex conjugates of each other. So the determinant is actually M positive. And then one can argue that if I introduce a term like this, which is more Hermitian in the kind of language you're looking at, so this in this non-relativistic form actually is solvable. Now in the traditional approach, although this determinant of this M is positive, as soon as you add terms like this and try to think about sort of a determinant of this whole term, there is no guarantee that that will be positive because of these fluctuating phases.
What is the relationship between the size without spin up and down and the ones with?
Oh, sorry. So in the first thing I have psi bar x up, psi bar x down, M.
Doesn't have chemical potential here.
You can add a chemical potential also.
On the difference, you have an unpolarized
Sigma 2
system.
is what?
You'll have probably a study in an unpolarized system. For unpolarized system, determine that it's positive. If polarized, it's
Particular
negative.
one?
Okay.
Yeah, but this is very similar.
It's like the BCS problem. It's the same action. So
No, it's
that
very
is positive.
similar to problem we have in nuclear physics where we use time reversal symmetry. And the Haberstone, which actually in that case
This
is
is
the
the
remaining variant on time reversal symmetry. So the
Mhm.
will come in complex conjugate pair.
It's
That's
very
exactly when we have a
simple.
good sign interaction. So very similar to
It's much
in
simpler.
time reversal symmetry.
It's much simpler. This is the BCS Hamiltonian, or the action for BCS.
No, it's more general than BCS. I mean, this is only one example.
I claim that with these interesting SB interactions with phi x and phi star, there is a whole class of models one can do. If you put an on-site interaction, of course, this reduces maybe in some cases to just the Hubbard model, the attractive Hubbard model. I agree with that. But with these phi fields, which can be dynamical, I think there are a whole class of models that one can solve, which are different.
Yeah, but this could be the auxiliary field, the usual approach if you have.
If you want, yeah,
Yeah.
you can think about this as the auxiliary field.
It's exactly the case where we have good sign interaction.
Right, but suppose it's not an auxiliary field, if you have dynamics of the phi, right, so then also it's solvable. All I'm saying is that. So there are many interesting lattice models which we now can solve. There are Yukawa models with Wilson fermions. There are gauged Nambu-Journal-Asenio models which were not solvable. There are also models inspired by graphene. Some of them had a sign problem before. We were able to formulate these without sign problems. And then new models of pairing interactions, which I just mentioned, are also possible. And then I would claim that there are also models with repulsive interactions that are solvable. And if I have some time, I will explain that at the end of the talk. So let me show you some results, because all this is of course good analytic work, but on the other hand, if you cannot do something practical with it, it's not that useful. But we were able to do some practical things. So this work has been done with Agni here. So we looked at some class of relativistic fermion models with 4 fermion interactions. So you can think about these as graphene inspired models. They are not on a honeycomb lattice, they are still on a square lattice, but then with staggered fermions you can actually show that these models have almost the right symmetries of, not the right symmetry, there's still a spin symmetry that graphene has, and then there are extra symmetries which in the QCD literature we call chiral symmetry, but it's some kind of flavor symmetry in 3 dimensions. And then there are different types of models that have been considered in the literature. One are called Sirring models, which just have a nearest neighbor interaction of that type. Since there's only one psi and one psi bar on each side, there's no psi bar psi squared, so the interactions are nearest neighbors. So that's sort of a general interaction of all different neighbors if you want. And these models are called Sirring models. They are actually solvable. There's no sign problem in the traditional approach. But then there are also other models where you can introduce more interesting interactions. For example, on a body diagonal or on a square, on a diagonal of each square, which I don't write because that can actually change the symmetry from a U1 to a Z2. So we can look at all these different Gros-Nouveau type models. And all these models are, of course, well known in the literature. They have 2 different phases. As you crank up U, there is a symmetric phase and there is a broken phase. And one of the interesting questions is, can you calculate the critical exponents at this quantum critical point, which separates the 2 phases. People have studied, so in this model there are past calculations, so I will compare some of the results with that. In this case the problem suffers from a sign problem, so people have not done it. They have been able to do it with some kind of doubling so that you can cancel the sign. There is one work where people did this calculation without just ignoring the sign problem, which we believe got the wrong results. I will mention that.
Can I ask a question?
Sure.
Is this 2 plus 1 dimension?
Yeah, this is 2 plus 1.
So then you see so if I look at the second cube, I have a non-locally timed interaction there. Is that correct? Because I think of the plane, you see, being the x, y, and this be the time direction. So I have this interaction at different times.
Right.
This
is not really you can say it's like a derivative in time interaction maybe. So this is just a nearest neighbor.
I want simply to clarify, because it's a typical interaction that you don't have in non-relativistic physics.
Fair enough.
You see, you need a carrier in order to have that in relativistic physics, and therefore you need another degree of freedom to attach to this model in order to make it so physical.
So let me explain the reason why this interaction is okay in this model. Is because we deal with a special kind of fermion called a staggered fermion. And in the staggered fermion, what happens is that the fermion degrees of freedom in the Euclidean space are spread out over a hypercube. So in that sense, the interactions over a hypercube can be thought of as just interactions of the same time slice. Think in the continuum limit, there will just be some interaction within that hypercube. So it'll couple some psi.
I was simply asking, you see, about the meaning of that, you see, not when you're going to use it. I want simply to clarify.
So assume that the following is the way I'm looking at it.
You did answer my question.
Okay, good.
I have one question. When you say ignore the fermion sign problem, it's not clear to me what you mean.
What do you mean?
When you you say that?
Yeah. So
Are
what?
you doing it wrong? Is that what it means?
So here is what it means exactly. This is what, because the paper doesn't explain this. This is what typically people do. So when they do hybrid Monte Carlo, this is what was done in that calculation. Typically, instead of determinant of m, they do determinant of m dagger m, right? And then they take square root and all that, and then in that sense they have ignored the sign.
I see.
That's what they do, and that's what they weight by.
Because the other way to interpret it would be the usual way I would interpret
Yeah, yeah.
it, which would mean you would just get a horrible signal of noise, but not the wrong answer.
I see. So this is interesting. So that's what it means when I say they ignore the sign. So they would just calculate, let's say, the square root of the determinant squared or something like that, or the magnitude of the determinant. So we looked at a few observables. We looked at one of the interesting things is the condensate that forms in these problems, and the condensate that is this is what is called the chiral condensate, psi bar psi. So we can look at a susceptibility of that condensate. Since there is a spontaneous breaking of a U1 symmetry, there are sort of conserved charge. So there are winding numbers of these conserved charges. So if U1 is breaking, this is like a superfluid density, related to the superfluid density if you want. So that is something that we looked at. We looked at the ratio of basically a Fermion correlator to measure the different critical exponents. And there are sort of standard finite size scaling, what happens close to the critical point, so that we can extract the critical exponents eta and nu from that. And these are some of our results. So we were able to go to 40 cube lattices, and there was a question of how we update things. So here we had to do determinants of 8,000 by 8,000 if I'm not mistaken. So that was doable thanks to Anyi's efforts. So we did a calculation, we used a combined fit, and these are sort of our results where we could isolate the critical point accurately and got the critical exponents with maybe within 1% or even less. So now let me compare with what we could achieve compared to what was done in the previously, right? Remember, this model was solvable using hybrid Monte Carlo. So these are sort of our comparison. So it was done in mean field theory long time ago, and of course you get trivial exponents there. It was done in the late 90s on small lattices, and the masses are sort of pretty high. And remember, I don't want to add a mass term to get the critical point, because this is a relevant perturbation and it can sort of destroy the critical properties, and so you need to really extrapolate to small masses to really get the critical point, and that's a pretty complicated thing for them to do. We were able to do exactly massless fermions without a problem, and you can compare the accuracy with which we were able to compute the critical exponents with our method. So it was and from what I understand, these exponents are maybe of some interest in graphene because of the symmetries. I can't quite be sure. That's something that's still debated. And interestingly, there is no epsilon expansion or anything that really produces these results. There are questions of exactly what the symmetries are, but these are the new exponents that we find for this particular transition. So there was this other model which could not be solved earlier, which had the same symmetries, lattice symmetries, but in the past people have studied as gross nouveau models, and it was thought that they belong to a different universality class. In fact, I've talked to some of the experts who have done this, and before we did our calculation, they would all suspect that it actually belongs to this different universality class. But interestingly, this model, of course, the critical point is at a different point, but then the critical exponents are all well within what we find. And so here is the first example where in a fermionic system, two completely different models which were thought to be in different universality classes are actually in the same universality class, not actually different. So for some, I would say that the fact that these two are similar is sort of surprising because of the previous work. And so the work that I'm talking about is, for example, these authors have done a lot of calculations with these doubled fermions where they could solve the sign problem, and they all get answers very close to the critical point. And then they all believe that, well, maybe the sign problem is not so important, and so one can actually believe that the Gross-Novo model and the Thirring model were at different universality classes. We find that in one of these models actually we do get a different exponent, and as I told you, there's this other work with a Z2 symmetry where they ignored the sign problem, and they also got very similar results. Their nu was quite close to 1, and we believe that the reason why they got that was because they ignored the sign problem. So we have repeated this calculation, not exactly the same model because there are just for technical reasons, but with exactly the same symmetry, and we get slightly different but almost the same exponents as that. So the conclusion we feel is that the sign problem is important even in these Gross-Novo models, at least close to the critical point. So one has to be careful about that.
Even the sign is important.
Sign, yeah, yeah, sign is important. Sorry. So that's. Let me conclude. I believe that the Fermion bag approach is an alternative method to solve some fermion sign problems. So there are many new sign problems that can be solved with it. Solutions require thought and understanding of the underlying physics, and this is something that is not quite appreciated, but I think that solutions to sign problems is an interesting field of research in its own right. It is at a crossroads of mathematical and computational physics, and I think this community will definitely appreciate it, but unfortunately this needs to be advertised a bit more. Thank you.
Other questions? Well, just a general question. So we sound very interesting models, you come up with that, you can avoid the sign problem by doing these big models and so on. But in a way you have to I mean, you come first with your interactions and you try to find a problem. I mean, like if I give you a problem, that is interesting to me, then this approach really doesn't help, right?
So as I told you, I think this is exactly the missing ingredient, right? So often sign problems are thought of as a computational difficulty for Monte Carlo methods, and people don't focus on it. So I think more thought goes into it. I think there are new ways of thinking about determinants, right? So we have one class of models which we think that determinants are all positive, but positive determinants come for various reasons, and I think not much thought has gone into what type of determinants are positive, and so can we reformulate our problem which of the interesting type. And so there is, I think, a learning curve, and unfortunately not many minds are thinking about it. They are working on exciting problems, but not with the intent of rewriting it such that we can really solve it using a computational method. So I don't know if there is time, I can mention a bit about this repulsive model, which I find quite interesting. So here is a simple spin half, two spin half species. I don't know what the physics is, but it's interesting to think about it. So think about, instead of a repulsive Hubbard model where you just have a spin up and a spin down, infinitely repulsive, think about two species of spin up and spin down particles. And now there is an infinite repulsion between these two spins, right? So then in this Fermion bag approach, one would think about the way to think about this problem is that there would be regions of space where the spin up species exists, and there are regions of space where the spin down species exist. And then there are determinants here and the determinants are there. Now if there is only a single determinant, that we cannot prove is positive. We cannot prove, but maybe there are some reasons at least to think about. But if there are two species, this determinant is just determinant squared, that determinant is just determinant squared, and so this completely positive partition function. So that's a model, if somebody has the time, could be simulated, and I don't know whether there is an interesting quantum phase transition. What is the physics of this repulsive model? I have no idea. If these determinants are single species, that is precisely the Hubbard model, the repulsive Hubbard model, but then there's no proof that this is positive. That's where the confusion is. So you see, there is a new way to think about the repulsion, what exactly it means.
Is one of those supposed to be labeled species 2?
Ah, yeah, thank you. Sorry for that.
But there's another type of sample that we encounter all the time in non-relativistic, well, in our problem. I mean, so there's one sample comes from the determinant, but also often if you want to get some a good quantum number back into the problem, you have to do projection. So like, you know, for example, to do canonical ensemble, project a good particle number or good angular momentum or good parity. And even if you have a good sign interaction, the determinant is positive, once you do the projection, for some quantum number you get a new sign problem, which is different from the traditional one.
They're,
One there is something you thought about, but I mean, that's enough.
yeah, I think they're all sort of completely related. I think they're all the fact that if it's a good sign interaction, sometimes the reason the sign problem is not there is because the lowest ground state is somewhat nice, right? That's why it's doable, the partition function is doable. But then when you project it out, now you're going to a sort of a higher energy state, and now there are all these fluctuations. So one has to, in some sense, I feel that's precisely what's happening with even in Hubbard models, repulsive Hubbard models, right? Because if you have no filling, then somehow it's easy, half filling, it's easy, but then as you go away from the filling, then you are sort of exploring other interesting ground states. And so then you get all these kinds of, so they're all not completely different, they're all related to the quantum interference problem. So one has to think about the underlying physics and see how to formulate that physics in a positive way. And
for the excited state, if you have a good sign, sometimes you can do it by looking at correlation function. That's what people do in lattice QCD. You look at the correlation function.
right, so it's very clear. For example, even if you add a few baryons, so the baryon chemical potential is a severe sign problem, but even if you have a few baryons, every time you introduce a baryon, then the signal to noise ratio is a big problem, and we have an expert here who has been working on the signal to noise ratio and these baryon correlators and understanding why that is true and all that.
Kind of definition, but I don't understand the distinction between auxiliary field and a dynamical field.
Oh, the only difference is that a dynamical field is more difficult to integrate over. An auxiliary field is just a constraint which you can, if you want, try to integrate over.
Kinetic term.
Exactly.
It propagates over distance, while the auxiliary field is just out of time.
So it's a non-local in
Yeah,
time,
exactly.
if you like.
Yeah,
In space.
space and time maybe.
So in a way, that seems quite powerful. I mean, a lot of things could be cast into that form.
Yeah, so that's why I claim that if you can solve, with this dynamical part for these 5 fields, I think the physics can become much more richer than the simple on-site auxiliary thing. So I believe that if you have an auxiliary field here, then you go back to the usual Hubbard model. But then if you have a dynamical field, maybe the physics of this dynamical field can also be quite interesting. So one can really explore more interesting phase diagrams. So it's not clear to me whether everything is understood. Maybe it is, but it does open up some interesting questions.
So Charlie, I'm trying to think of this from an algorithm point of view.
Yes.
So you have these Fermion bags, and their locations determine the determinant that you need to calculate.
Right.
So I can see. I assume that in your algorithm, what you did with Ani, you calculate the determinant exactly.
Right.
Now, if I wanted to do a fair estimator of the determinant, the question is, do I need to have that converge within one loop? In other words, do I need to nest the algorithms within each other, which would be a big hit computationally?
So what we do is, at least practically what we do is, since often we have to change something locally, this may be not the best way to do the thing, but when we do locally in this whole big determinant, only one row and one column get changed, right? So we can, we have done the work for the determinant before, and this extra work is scales much less.
So you have to store all the cofactors in any case.
Yeah. So that's so Ani wrote a nice code which stores all that information and just.
I see, but I'm trying to think. Suppose I want to calculate the determinant using pseudo-Fermion methods or something like that.
Right.
Using hybrid Monte Carlo. The question is, if I keep changing which columns and rows I'm deleting, would that actually work or not? Because that's sort of an abrupt change. It's not really.
Right. So I think if you do a hybrid Monte Carlo and delete and insert a bond or a monomer, this can be quite a big change. So it's not clear how to do the hybrid Monte Carlo. So we have not thought about it. So that's an interesting sort of question to think about. But on the other hand, at least for a class of problem just removing, and we find it pretty stable, because in fact we can, what we do is we take regions and we say we are going to only update in that region, so that all the big region is almost fixed, right? So there are only, out of 8,000 bonds or 8,000 by 8,000 matrix, we only update 100. So that saves us quite a lot of speed. And then if we go to another region and recalculate the determinant, up to machine precision, we get exactly the same determinant. So we know that we have stability on that.
Do you see a sort of upper limit to the size of the regions that matter at this point? I mean,
Upper limit to the size of the region.
The size, yeah, I mean, if you take these determinants, which are essentially sub-determinants,
Right.
in the so in principle, I mean, you get contribution from determinants of any size,
Right.
Is that strictly so, or I mean, you can sum up to a certain point and then you see that maybe contributions coming from determinants
Bigger, yeah. So this is another thing that we have not yet explored, I would say. At strong coupling, the determinants can be pretty small, so you can.
Yes, then you show
So
that
yeah.
essentially.
But on these interesting critical points, these determinants are sort of the bags sort of permeate throughout, right? So you can't really use that efficiency. But on the other hand, you're right that clearly there must be some, as you go to farther and farther, if you change something, something must decay down. Now, since we are exactly in the massless limit, we didn't want to sort of, because there could be power law correlations which are important.
Yes.
But on the other hand, one can perhaps imagine some slightly variant of this, but that would be sort of an approximation, or maybe there's some other trick one can use to sort of sample the determinants in a more interesting way. Yeah, that's something we have not thought about, but that's something to think about.
Any more questions or comments? If not, okay, I've been asked to keep the talks as scheduled, so we try to comply with this, and so we reconvene, okay, at 11:30, okay, for the next talk. Thank you, Shailesh.
Thank you.
This particular example is exactly what we have in the non-relativistic.
Which one?
When you write down this kind of action.
Mm-hmm.
Yes.
So in our case, to do a non-relativistic problem with